All right, let's get started at 11 a.m. Okay, so welcome to lecture 7. Hopefully, you all had bless you, you had a wonderful 3-day weekend. Normally, or I say normally, I guess what I should say is for my past 10 years at Marshall, in the fall semesters, we would only be granted that one 3-day weekend, and then it's, full schedule all the way to Thanksgiving, and now we have that October break. So we have another 3-day weekend in store, although that's a little while from now. So maybe that'll make the semester a bit more refreshing. Let's see. So today what we're going to do, this is kind of funny, but we're actually going to do some statics today. And what I mean by that is we actually haven't really been doing applying principles of static equilibrium up until now. We have been doing a lot of stuff, but we haven't actually been doing any statics. Like, we go through a math review, a physics review. We talk about vectors and how to add vectors, but that's not statics. Let's talk about statics. So that's what we're going to do today is we're going to review what does static equilibrium mean, okay? We're going to do it, so the way that we do it in this class is we start basic and then we get more and more advanced. So we've been doing problems that, again, involve statics of particles, okay? And that's just a shorthand way of saying that all the forces all meet at a common point. And in 2 dimensions, we have 2 equations that we're going to have to satisfy. And so what that means is that we're going to have 2 equations and 2 unknowns types of problems. That is a problem that you have done before, but it might have been a while. So we're going to do a quick algebra review today, and then we're going to start applying principles of static equilibrium in 2D. Once we figure out 2D, we'll then go to 3D, and then take it from there. So yeah, I think you'll see sort of a natural progression of things moving forward. Before I move on, everybody get the code? Everybody got the code? All right. So let's get into static equilibrium. Okay. But I find it valuable to sort of cover the requisite math first, because I don't want to, here's the topic, and oh, by the way, here's this math on top of it. Let's get you in the right headspace so that when we start doing the problems, oh, okay. So I want to review how to solve 2x2 systems of equations. You might not have referred to it that way, but you have done it before. Okay, so let's look at systems of simultaneous equations. Okay. Here is a simultaneous equations problem, okay? So let's assume that I give you this, okay? So I give you 2 equations. I say that x plus 2y equals 3 and 2x plus 3y equals 4, okay? I give you those 2 equations. And the goal is to find those magical values of x and those magical values of y, that one pair of x and y values that satisfies both equations, okay? Has everybody done a problem like that before? It might have been a while, but everybody in here has done a problem like that before. This is one of the most fundamental foundational problems in all of mathematics, okay? There is an entire field of study devoted to just problems like this. The name of that study is linear algebra. Have you ever heard of linear algebra? That's what linear algebra is. It gets its name from the fact that you could rewrite this as the equation of a line and rewrite this as the equation of a line. And so graphically what we're trying to do is figure out where the lines intersect. And there's only one point that they intersect, right? That one point, that one value of x and y where both equations are satisfied. Linear algebra gets its name from the fact that, this is a 2x2 system of equations, but many mathematicians and engineers deal with a million by a million problems. And so being able to solve that and wrap your head around that happens actually more frequently than you think. Okay. So these are the types of problems that we're going to be looking at. There are, I would say, 3 practical approaches. In all honesty, as the systems get bigger and bigger, there are more ways that you can go about this. That's sort of what a linear algebra course is all about. But what I'll say is that there's 3 practical approaches: substitution, elimination, and then honestly using that matrix algebra. But for 2x2 systems and 3x3 systems, which is pretty much what we're going to be dealing with, your calculators do this job for you. They do it very beautifully and very wonderfully. So I want to walk you through how that works. Okay. Let's talk about this. So let's take substitution. Okay. So how does substitution work? Okay. So I've got this system of equations. Here's the method of substitution. The first step is to pick one of the equations and rearrange it. And rearrange it such that I've isolated one of the variables. Okay? So if I take the first equation and I say x plus 2y equals 3, I can isolate x. Just move the 2y over to the other side. Say x equals 3 minus 2y. And then the method is substitution, right? So what I'm going to do is I'm going to take this x equals this pile of junk here, and I'm going to take that and substitute it into the second equation. So where the second equation is 2x plus 3y equals 4, where it says x, I'm going to say, no, let's not put x, let's put this, because that's what this equation says. Then I do a lot of algebra hullabaloo, distribute this, collect terms, rearrange, and by golly gosh gee, I get y equals 2. And so there's one answer. I love my technical terms, my by golly gosh gee and hullabaloos and holojumps, right? Very technical terms. Right? Now that I have y equals 2, I'll take y equals 2 and plug it into either one of the equations. It doesn't really matter which. So let's do it in the first equation. So here's y, here's 2, rearrange, and I get x equals -1. So I propose that x equals -1 and y equals 2 is the solution. It is the only pair of numbers that will satisfy both equations. And just take a look. So I have x plus 2y equals 3. That's -1 plus 2 times 2. That's 3. What about the second equation? Double this is -2. 3 times that is 6. 6 minus 2 is 4. There is only one pair of numbers that satisfies both equations. And that's the pair. Should be pretty straightforward, right? Okay, that's method 1. Here's method 2. Method 2 is elimination. Okay, so here's what method 2 is. Method 2 is really how computers do it. When I actually boil it down, if you were to break out MATLAB, which I know that for many civil engineers is akin to mentioning Lord Voldemort at Hogwarts, but shall not be named. But essentially, that's how software programs solve matrices, is that what they'll do is they'll look at one of the equations and figure out what do we need to multiply that equation by. So it'll pick this magic number, in this case -2. So it takes the entire equation and multiplies it by -2. So instead of x plus 2y equals 3, it's -2 minus 4y equals -6. And the reason that we do that is because this -2 in front of the x matches the +2 in front of the x on the next equation. And so what we'll do is we'll add the entire equation, set of equations together. So here's equation 1, here's equation 2, add them term by term. What's that plus that? 0. What's that plus that? -y. What's that plus that? -2. Solve for y, we get y equals 2. And then substitute that. We can either repeat it for the other variable or substitute it back in, and we get the same answer as before. That is another way of doing it. And again, most software programs will use a method akin to that. I think what MATLAB does for most modestly sized systems of variables. All right, so far so good? Okay. Speaking of, the third is to use matrix algebra. Okay, so the way matrix algebra works is what we do is we rewrite the system into tables of numbers. Okay, so what we'll do is we sort of rewrite it in this format. Have you all seen this before? Imagine a lot of you probably have. So we write a square matrix, and the square matrix contains the coefficients of all the terms in the equation. We have our unknowns, and then over here, it's whatever's left over on the other side of the equal mark. And then, so the expression, or the way that we've written the formula is AX equals B. So A is this square matrix, and B is this column of stuff on the other side. And in order to solve for the unknowns, what we do is we just invert this matrix, multiply it by that. Now, inverting a matrix is actually a very daunting task when matrices get bigger and bigger and bigger. There's a very plug-and-chug expression for 2x2 equations and for 3x3 equations. After that, it gets a little messy. And again, that's sort of like, if you ever take linear algebra, that's sort of like a big point of the whole class, is just how to figure that out, whether or not matrices are even invertible to begin with. Again, another story for another day if you take junior level math class. Okay. Fortunately for us, and for most basic applications, we can do this either inside a software program or inside a calculator. Most of you will probably have calculators on hand that can do this. Okay. Now I want to show you something real quick. Okay. These slides, let me get out of this slideshow real quick. These slides are going to show you how to do this on the Casio FX115ES Plus, which is what most of you learned on in Engineering 111. Am I right? Okay. If you have another calculator besides that, what I've done is if you go onto the course shell on Blackboard, if you go into lecture notes and supplements, if you go into the particle statics, you're going to see this link. Okay. What I've done here is if you click this link, it's going to take you to a YouTube playlist. And what I've done is I've collated a list of videos on how to solve systems of equations with calculators other than the Casio. So I'm hoping between what I'm showing you in these slides and what I've got here, that you should be able to do it on just about any calculator that you've got. Okay. I'm going to follow the Casio because it looks like most of you have one. I'm just by eyeball. But if you have another calculator, this playlist will show you how to do it. So far, so good? All right. So let's show you how to do it with a Casio. So the way that it works with the Casio is you hit the mode button. The mode button will bring up this menu right here. Whenever you're standardly operating the calculator, you're in mode 1. That's the computation mode. So like if you're just opening the calculator and want to do some basic math, that's mode 1. So once you're done with this, go to mode and hit mode 1, and then you're back to regular mode. We're going to go to mode 5 for equation solution, and it gives you 4 options. Option 3 is the quadratic formula. Option 4 is the cubic formula. For this, we're going to use either options 1 or 2. Option 1 for 2x2 systems, option 2 for 3x3 systems. So if you wanted to follow along with this example, what you would do is you would say, let's do option 1, and then you get a little table that pops up, and your table is going to look like this. It's going to be 1, 2, 3, 2, 3, 4. And where did I get those numbers? That square matrix and that column. So 1, 2, 3, 2, 3, or 1, 2, 3, 2, 3, 4. Then once you've entered those in, press the enter key again, and it will say x is minus 1, y equals 2. Now what the calculator is doing is it's saying x and y. What it's really saying is the first variable and the second variable. And that's going to depend on how you order things. That'll become clear when we do an example here in a little bit. But the calculator doesn't know what you named your variables. But as long as you've got accurate bookkeeping, you're going to be fine. So, everybody good? Okay. Any question about these types of problems? Okay. So now let's talk about static equilibrium. Okay. Now that we've got that out of the way, let's talk about static equilibrium. And particularly, we're going to talk about static equilibrium in 2 dimensions. So we're going to be treating things in 2D. And so I actually kind of want to focus on this upper image right here. So this is an image of a large overhead crane picking up component in probably like a manufacturing or a foundry type setting. And so we have this crane picking up this pretty heavy object, lifting it up. This is a perfect example of a static equilibrium problem, assuming, for example, that the crane is stationary, that the object is not moving. So again, what does it mean to be static versus dynamic? Static situations are bodies at rest or at a constant velocity, i.e. no acceleration. Dynamics is when they are accelerating. So in a static situation, we would want to ultimately figure out, if we're lifting this up, maybe what's the tensile force in each of these cables, and how would we figure that out? We would apply equations of static equilibrium. I've been talking about this. What are equations of static equilibrium? Again, okay, let's go back to, so let's take a step back and let's go into vector addition. So if I have a bunch of vectors all applied at a common point, up until now, if I mentioned the term resultant, you would know what I mean. The resultant is if I take the vectors and let's say I describe them in IJ notation, I sum up all the x components, sum up all the y components, and I now get a new vector which we'll call R, which is the sum of forces times I plus the sum of the forces in the x direction times I plus the sum of the forces in the y direction times j. That is the resultant vector. Everybody with me on that? So the idea is if I have a point and there's 12 forces all going through that point, I can replace all those 12 vectors with just a single vector, and it would have the same equivalent action. So far, so good? I propose that if you recall, what is statics? Statics is a situation where the bodies are at rest or at a constant velocity. Well, Newton's first law says that an object is at rest, will stay at rest until it's acted upon by an outside force. But if it's already at rest, I propose that the sum of the forces must be zero. Okay? So what are these equations of static equilibrium? That. For static systems, the resultant for the system must be zero. Okay? So how does that relate to what I just spent the last 10 minutes talking about? Well, it relates to this. If the sum of the forces must be zero, how do I get the sum of the forces? I get the sum of the forces in the x direction times I plus the sum of the forces in the y direction times j. But if each of these have to be zero, look what I got. I have two equations, and I will probably, for the problems I'm dealing with, have two unknowns. So these are going to be the types of problems that I solve. Okay? Everybody with me so far? So far, so good? Okay. The only thing that I want to make sure that I throw in here before we start jumping into problems is that very possibly either on problems we do in class, homework problems, or celebrations of learning, keep in mind we are dealing with forces. Forces. We are not dealing with masses. It is very common to say, hey, determine static equilibrium for this thing, and you're given a mass of 50 kilograms. Don't forget to multiply it by gravity, okay? Remember, gravity in SI is 9.81 meters per second squared and 32.2 feet per second squared in US units. Many problems are going to reference an object's mass instead of its weight. So don't forget that. It is a very easy thing to forget, okay? Sound good? Let's have some fun. Let's do this problem here. Okay, so let me pull this up in the notebook. So here's the problem we're going to look at. So I have a weight here that's 400 pounds. Okay, it is being supported essentially by these two cables that are hanging up at an angle. This cable, we'll call it AC, and this cable BC. Okay. And so what we're going to do is we're going to determine what is the tensile force in this cable and in this cable to keep this block in static equilibrium. In other words, we want the block to sit still, okay? And note, we don't have to worry about gravity for this problem because it's already written in 400 pounds, okay? Okay, I'll give everybody a sec because I know some folks are drawing some stuff out. That is totally cool. While you're drawing this out, let's see if we remember this. What is this angle going to be? Say it again. 30 degrees. And this angle? 50 degrees. Okay. Just want to have that out there. Now, like I said, this first unit of the class is called statics of particles. And a particle is just a shorthand term for a concurrent force system. When all the forces all meet through a common point. Okay? So what we are going to do is draw a diagram that shows all the forces meeting through this common point. The point we are going to select is point C. Does everybody kind of see why we're choosing that one? And all the forces are going to go through here. We've got this force, and this force, right? Okay. So there is a name for this diagram. It is called a free body diagram. A free body diagram illustrates all the forces acting on a given body. I imagine you might have heard that term in physics, the term free body diagram. So that's kind of what that is if you haven't heard that before. Okay. So let's draw a free body diagram. And what I'm going to do is I'm going to draw the free body diagram over here. Okay. And so we're going to look at, call it right here, point C. Okay. I propose that there are three forces going through point C. Okay. Now, Okay. The first one is going down. Okay. I'm going to call this W. And I'm calling it W because I'm using that for weight. Okay. Because that's the weight of this block here. Okay. But I've got two forces that are going like this. Let's call this a tension, and this one as well, but let's call it tension AC and tension BC. I'm drawing these blue because I'm sort of saying my red are my known forces and my blues are my unknowns. But that doesn't really matter, at least for our purposes here. Then we've got that. Okay. Okay. So far, so good? Okay. Okay. Now the next thing I want to do is I want to describe these vectors. And describe these vectors, when I say that, what I mean is I want to formally write what these vectors are. Okay? I want to actually write what they are. Okay, so let's start out with tension AC. Okay. All right. So okay. So look what I'm doing here. I'm saying tension AC equals a pile of junk times I plus a pile of junk times J. Okay. Okay. So let's see if we can work through this. All right. First off, this angle is 50 degrees. So that means I need a cosine in here and I need a sine in here, right? Okay. So I need okay. What else is missing inside those blocks? The magnitude, right? Now, I don't know what the magnitude is, so I'm going to leave that as a variable. We'll call this TAC, right? I mean, how do you write a vector, right? It's the magnitude times cosine for I and magnitude times sine for J, okay? Now, is there anything else that's wrong with this? This is negative, right? Because it's pointing to the left and up. So this is negative, this is positive, right? So I need a negative here. Is that right? Everybody okay with that? So let's do the same thing for the next one. Okay? So tell me what goes in this box. This one right here. There you go. TBC cosine 30. And what about this one over here? Should be pretty easy, right? What's the deal with the signs? Positives, negatives? What's going on with that? They're both positive because they're both in quadrant 1. So far, so good? Okay. Now, I'm going to do the same thing also. I mean, how many vectors are going through point C? Not 1, not 2, but 3. So there's a third one too. Okay? What goes in here? 0. What goes in here? Say it again. Negative 400, right? Negative 400 because it's going down. So 0, negative 400. Is that a fair statement? Okay. So what I am saying is this. Here's what I'm saying. I drew myself a nice little red dashed box. What would happen if I were to add up these terms? If I were to add up the terms in that red box, that would be the sum of the forces in the x direction, right? What if I were to add up everything in my little dashed blue box? That's the sum of the forces in the y direction, right? Make sense? So if I now look at it that way, I can now start applying equations of static equilibrium. So what does equations of static equilibrium mean? If I add up everything in the red box, what should it equal? 0, right? So the sum of the forces in the x direction equals to 0 means the following. It means that, right? That plus that is 0. Here, maybe I'll be formal about it. I'll say plus 0 equals 0. Okay. Now, here's what I am going to do, and there's a reason why I'm doing it. I'm going to rewrite this like as follows. Basically, what I'm doing is I'm taking the variables, I'm sticking them outside the parentheses, and I'm preserving everything that's inside the parentheses, all my signs there. And I'm mainly doing that for like an aesthetic visual representation so that when I write this in matrix notation, I make sure that I haven't forgotten a plus or a negative somewhere. Okay. Well, let me, sorry, I scrolled too much. Let me try and do it like that so that we can see what's going on. Now, what I'm going to do over here is I'm going to say this. Oh, I just realized I didn't put a unit here on the 400. Have I shown you all this before? Did I show you all that? What's that? Pound symbol, yeah. So it's 400 pounds. So we'll put that there. Okay. So, all right. So let's do that full column. So TAC sine 50 degrees plus TBC sine 30 degrees minus 400 pounds equals 0. Now, here's what I'm going to do. I'm going to do the same thing I put up here, put all my terms outside the variables in parentheses, but I'm going to also move any constants over to the other side of the equation. Okay? And you'll see why I'm doing this. Again, it looks, I am sort of repeating the step. but I'm doing it for a very specific reason. So now I have, yes. Because it's in static equilibrium. That's what static equilibrium means, is that in order for this to be in static equilibrium, they have to be zero. So whenever we're saying that this system is in static equilibrium, what we're trying to do is figure out what must this value be and what must this value be for these to be true. That's so static equilibrium, whenever that's said, that's what that means. Later on we'll have a third equation. We'll have sum of forces in the z direction equals zero when we do this in 3D. And even later on, when we deal with rigid bodies, we'll have sum of forces and then sum of moments will be zero as well. That's way down the line. Okay. So now what we're going to do, we have two equations. We have two unknowns. So now let's solve the system. So here's what I'll do. Wait, whoop. Forgot it. That's supposed to be sine. That's supposed to be sine. I'm getting ahead of myself. So you all don't really have to write that again, but I'm doing it just to make sure that you can see how I'm translating this into matrix notation. So basically I've got the equations written sort of on top of one another, and I've got all of the positives and negatives preserved inside the parentheses, so that now when I rewrite this, I'm rewriting it as follows. Then sometimes what I'll do is I'll sort of do this, just to sort of separate the terms. I don't think I don't want to get two parentheses happy. So now what I've done is I've written this into matrix notation. And I've done that so that when I start using the Casio, I can now input the values pretty easily. Okay, so let's walk through Casio land. Let's see what happens there. Again, I'm going to do it the way the Casio does it, but if you have another calculator, I put stuff on Blackboard to walk you through that. So what you're going to do is you're going to say, the mode, then 5, then 1. And then the table that you're going to enter is going to be and the calculator will spit out an X and Y solution. Okay. I'm curious to see if anybody is getting that solution for those of you that brought your Casios. So again, you press mode 5-1 and then enter these in. And then when you've got your last value in, enter, just press enter. And it should give you a value for X and a value for Y. And if you have them, give that to me in 2 decimal places. 351.7 what? Bless you. 351.74. And then the Y comes out as what? You get that? Everybody else get that? If you did not, check to make sure. This is actually probably one of the biggest mistakes, that you forget this negative right here. Okay. The other thing is your mode, calculator in degree mode as opposed to radian mode. Okay. And again, if you have another calculator, I put a playlist on a Blackboard to walk you through how to do this. Okay. Everybody with me so far? Okay. Now, when we wrote the equations, we were very methodical in the order in which we wrote them. For example, equation 1 has TAC first, then TBC. TAC, then TBC. And if you notice, we were very methodical throughout the whole problem to preserve that order. We wrote the vectors in that order. Okay? The calculator does not know what vector is X and what vector is Y. But what it will do is spit out the first magnitude as X and the second magnitude is Y. And so what I am saying is that this, for our problem, is going to correspond to TAC. This is going to correspond to TBC. So therefore, that's going to be our answer. A couple of things about these answers that hopefully will give you some assurance that they're correct. Does anybody notice something about these two numbers? Okay, that's right. First off, this is a 400-pound weight. I don't have a value that's like 9,000 pounds and one that's 3. They're both reasonable numbers for holding up a 400-pound weight. But here's another one. They're both positive. They're both positive answers, right? It's a tensile force. And we're going to talk a little bit more about this later, but essentially what we did at the very beginning of the problem is we assumed that these cables were in fact in tension. Bless you. We calculated an answer and we got a positive value. That means that we're right, they are in tension. If you got a negative answer for a tension force, something would be wrong. Something wouldn't make sense. Is everybody with me on that? So the idea of assuming directions and the idea about that will become very relevant later when we start doing structural analysis and more applications of statics a little bit later. But for now, just know that if we're doing these tension problems and we're getting negative answers, probably something's off in your calculations. Okay. Any questions? This isn't bad, right? But this is our first real application of statics, right? We figured out what the forces needed to be to achieve a certain outcome, and that outcome was static equilibrium. What is static equilibrium? That some of the forces in the x direction are 0, some of the forces in the y direction are 0. We'll have, I think, one more day of practice on this, and then next week what we'll do is we'll extend this into the third dimension. Really, the third dimension is no more difficult than the second dimension. Or the 2D problems and 3D problems have the same inherent level of complexity. Really, the only thing with 3D problems is that they are a little bit longer. And the other thing about 3D problems is that actually getting to this point right here, just describing the vectors, does take a little more work. With 2D, we can sort of just look at it and say, here's the vector. 3D, you got a little bit more work to do there. So we'll get to that point later. I am giving you 10 minutes of your life back. I'm going to pull up the QR code one more time, but that's all I have. I will see you all on Friday. Yes. Sorry. Yes. Yes. All righty.